So let's review. All orbiting objects orbit other objects in elliptical orbits. Ah, the beauty of the English language. It reminds you of how much money a woodchuck would chuck if a woodchuck could chuck wood. But anyway, moons orbit planets, planets orbit stars, stars orbit other stars in systems we call binary systems, clusters of stars orbit the center of mass of the cluster, stars orbit the center of the galaxy to which they belong, and groups of galaxies orbit their common center of mass, sometimes even colliding with one another if they get too close. Now, Kepler showed us how things moved. We discussed his laws of planetary motion in the previous videos, but it wasn't until Newton came about that we finally understood why things moved the way they did. Not only did Newton introduce his own laws of motion, he also explained the concept of universal gravitation. Newton's 3 laws of motion can easily be remembered as the law of inertia, F equals ma, and the concept of action-reaction pairs. So let's take a closer look at each of these. Newton's first law of motion, the law of inertia, states that an object in motion will remain in motion, whether that motion be no motion at all, or moving with a constant velocity in a certain direction, until acted upon by an external force. So an object at rest remains at rest, and an object in motion will remain in motion until, of course, acted upon by some external force, which causes a change in that object's motion. Our friend Wile E. Coyote here is unlucky enough to be testing Newton's law of inertia. Seconds before this moment, he was running off the edge of the cliff after the Roadrunner, but now he's about to find out exactly what happens when gravity takes over his motion. Not the best ordeal for him to be in, but let's move on to Newton's second law of motion, which states that the acceleration of a body, generally meaning any object experiencing motion, is directly proportional to the net force, or the total force, acting on it, and inversely proportional to its mass. So if you were to kick a ball, how fast it moves depends on how hard you kick. Newton's second law is often associated with the equation F equals ma, where F is the force applied in units of newtons, abbreviated with a capital N, m is the mass of the object in kilograms, and a is the acceleration that it experiences under this force in units of meters per second squared. This artwork, featured in an article from author Jolie Cannoli's blog, Jolie Cannoli and Friends, is an easy reminder of what each of the variables in Newton's second law represent: force, mass, and acceleration. In our next video, we'll take a closer look at how to use this equation with some examples, but first, let's finish up Newton's laws. Now, Newton's third and final law of motion states that for every action, there is an equal and opposite reaction. When one object exerts a force on another object, the second object exerts an equal force back on the first, just in the opposite direction. So if you push on a wall, the wall pushes back on you. A great example of Newton's third law is a rocket launch. NASA's Classroom Connections Rocket Races activity explains that a rocket engine produces thrust through action and reaction. The engine produces hot exhaust gases which flow out of the back of the engine. In reaction, a thrust force is produced in the opposite direction, lifting the rocket up off the ground. So now that we've been properly introduced to Newton's laws of motion, continue on to the next video to see some examples of using F equals ma, Newton's second law.